This video introduces you to shell sort, which is a special variant of insertion sort. In the previous video, we discussed that insertion sort in the average case takes roughly O(n) square execution time. Shell sort performs way better than insertion sort as it takes roughly O(n) 1.5 or O(n) 3 halves in terms of execution time in the average case. So the idea behind shell sort is that instead of sorting the entire array, we actually sort many smaller sub-arrays first using insertion sort, and then we perform insertion sort after we have sorted these smaller sub-arrays which are separated by some distance called a gap. This gap is generally of the form of a function, which is like it could have a series of numbers, or it could be just like a function that's dependent on the size of input n. And different books or different authors or different computer scientists has played around with this gap function, which really changes the execution time of this algorithm. So this algorithm is named after Donald Shell, who was a scientist, and hence it has this name. So let's see a quick worked example of shell sort, and then we are going to see the pseudocode and the time complexity of this algorithm. So how this works is like we have this initial array. Our gap function is something like n divided by 2. We have used this gap function, but it could be anything. So let's say if it was n divided by 3, we have to stick with this gap function throughout our algorithm. So we cannot have like in one pass we have n by 2, in another one n by 3, or in the next one n factorial or something like that. So the gap function should always remain the same. So how this works is, for the first pass, the gap would be n divided by 2. For the second pass, it would be n divided by 2 divided by 2. And then for the third pass, it would be n divided by 2 divided by 2, and then this entire thing divided by 2. So basically, at every pass, you use the previous gap in the form of the n variable. We keep repeating this process till our gap size becomes 1. And when we have a gap size of 1, this algorithm behaves exactly similar as the insertion sort, which is we just have one pass of insertion sort. So how this works is like initially we have a gap of n equal to 2, which is here n is 8. So 8 divided by 2 is 4. So what we are going to do is we are going to compare all numbers that are distant from another numbers with a gap of 4. So what we are going to do is we are going to compare 7 with this 2, because we have three numbers in between, or there's a gap of 4. We are going to compare 4 with 8. Then we are going to compare, just a second, 9 with 6. Then finally 3 with 5, because they are at a gap of 4. So in the first pass, what we are going to do is we are going to compare each of them. If they are out of order, we are going to swap these numbers. So in this case, 7 and 2 are out of order. So we are going to swap these two, which is 2 and 7 would be replaced. 4 and 8 are in order, so we don't care. 9 and 6 are out of order, so we swap. And then 3 and 5 are in order, so we don't care. So we have made two changes right here. Now we are going to like make sure we have like this is our array at the end of our first pass of shell sort. So this is how it looks like. Again, we have made two changes. One is right here and the other one is right here. Next, at the next iteration, we'll have gap equal to n divided by 4. So in this case, our gap will be equal to 8 divided by 4, which is 2. Now what we are going to do is we are going to compare elements at a distance of 2, which is they should have one element in between. So 2 will be compared with 6, 4 will be compared with 3, 6 will be compared with 7, 3 will be compared with 8, 7 will be compared with 9, and 8 will be compared with 5, and so on. So what we are going to do is we are going to start with 2 and 6. They are in order, nothing happens. We move our pointer to 4. 4 and 3 are out of order, so we are going to make a swap. So 3 will come here and 4 will go right here. So we have made a swap. Next, we are going to move our pointer to the next one, which is 6, and 6 and 7 are going to be compared. So we have 6 and 7 that are being compared. Since they are in order, nothing happens. We move to the next one, which is 4. 4 and 8 are compared. In order, nothing happens. 7 and 9 are compared. In order, nothing happens. Now we have 8 and 5. Here, there is supposed to be a swap, which is 5 and 8 are uh, not in order. So we are going to swap it. Now, one thing you have to note here, like the catch here is that if we make a swap, we have to see, like we have to go back to the previous gap place and check out whether it's at its correct place or not. So in this case, like once we have moved 8 5, we haven't finished this pass. So what it's going to do is it's going to compare this 5 with the previous element, which is at a gap of 2. So in this case, 5 and 4 are in order. So we stop right here. Let's say if this number was something like, let's say if this was 8, in that case, we would have swapped these and then we would have gone further back. But since they are now in order, the previous element is in order, we stop right here. So like why we didn't go in other ones, because they were already like sorted, which is both of those arrays or sub arrays were already sorted, so that's why we didn't go behind. And in one of the examples we saw that there was a change. I think it was this one second. So it was 2 and 6 was compared, 3 4, then 6 7 4 8. Okay, so there were no changes, so that's why like there was just one. So if the change occurred like right here, then we don't have to go further back, because in that case we do not have any elements in the back. So we keep going backward till we reach the front of the array. Let's now see our other example. So in this case, 8 and 5 were swapped, and now 5 is being compared with the previous element, which is 4. Since they are in order, nothing happens, and we have our final array at the end of second pass. Now we have n divided by 8. N is 8, so we have a gap of 1. In this case, this is the final pass, and this is actually equivalent to one pass of insertion sort. So technically what is happening here is now we are going to compare adjacent elements which are next to each other. So since 2 and 3 are in order, nothing will happen. Next, we are going to compare 3 and 6. In order, nothing happens. Next, we are going to compare 6 and 4. In this case, they are out of order, so a swap will happen, which is 6 goes right here and 4 goes right here. Now, since we made a swap, we still have to compare back 4 with the previous element. So in this case, it's already sorted, so we do not have to go back further in the left. Next, what we are going to do is we are going to compare 6 and 7. So 6 and 7 are already sorted, nothing happens. Now 7 and 5 are compared. Here again, there is like they are out of order. So we are going to swap these, which is 7 and 5 will be swapped. Now 5 will be compared with 6 because that's its previous element. So what exactly will happen is 5 and 6 are compared and they are out of order. So we are going to swap these two, which is 5 is here and 6 is here. Now 5 will be compared with the previous element. Since they are in order, we can stop right here. Next, we'll start from where we left, which is we finished our process till here. So we are going to compare 7 and 9 in order, nothing happens. 9 and 8 are compared. In this case, 8 and 9 are out of order. So the swap will occur. We have 8 and 9. Now 8 will be compared with 7. Since they are in order, we'll stop right here. We don't have to keep going towards the left. So in a way, at in every iteration or every pass of this algorithm, what we are technically doing is we are performing an insertion sort at a distance of this gap. And after we have done like this multiple times, at the end we'll perform insertion sort, like one pass of insertion sort in the final array. The intuition behind this is like the idea behind this is, let's say if there were many elements that were randomly sorted here. So what will happen is it will move some of the uh, elements that might take like much more swaps in the insertion sort and move it in the front way earlier than the insertion sort. So that's why like it behaves better. So most of the analysis for this algorithm has been done experimentally rather than mathematically. So we cannot make like claims on like what is the best or worst time case complexity. It is more experimental rather than theoretical. So at the end of our algorithm, we'll have this array which is sorted after our gap reaches to 1. So here's the algorithm for the shell sort. We initially set the value of the gap to n divided by 2, and then we run our outer loop or our pass loop till the gap is greater than 0. Within this, we are going to check for each array element from position gap to last element. We are going to insert this element where it belongs in the subarray. If the gap is 2, then we are going to set it to 1, because we know like once we have reached the gap 2, like next time it will be gap divided by 2, which is in case 1. Otherwise, like gap is gap divided by 2.2. So like this value is shown in the Markwise book, like they have followed this number, which is gap is equal to gap divided by 2.2. They come up with the number based on some experimentation, which is more optimized compared to um, n divided by 2. So we use like n divided by 2, but in the actual algorithm, they are using like n divided by 2.2 in the implementation. You can write in the pseudocode any one, which is you can divide the gap by 2. That's absolutely fine. So the general analysis of selection sort is an open research question problem in computer science. It's still like most, as I just discussed, the analysis actually depends on the execution, like based on experimentation rather than theoretically proving some time complexity. And the performance depends on how the decreasing sequence of values of gaps is chosen. So it depends on the function that we choose for the gap. So if the successive powers of 2 are used for the gap, then performance is O n square. If the successive values for the gap are based on something called Hilbert sequence, which is named after a popular scientist, the sequence basically has this 2 to the power k minus 1, where k could be any like integer. So in this case, it will be the sequence will look like 1, 3, 7, 15, 31, and so on. Then the performance can be proven to be ON 3 by 2. So it's beyond the scope of the course, like how we are going to prove this, but like I'm just like letting you know that the performance in terms of average case typically would look like ON to the power 1.5 or 3 by 2. Some sequences might have like better or worse performance based on the gap function that you might take. So in the worst case, it's going to perform like O n square time to execute the algorithm. In the average case, it's roughly O n 5 by 4th, which is O n to the power 1.25, or n to the power 1.5, which is 3 by 2, depending on the sequence. And in the best case, this is roughly n to the power 7 by 6, which is actually a little bit worse than the insertion sort in case of best case, because in that one it was ON. So like that's a trade-off, which is, but typically we won't have best cases. Typically when we are writing code, we deal with mostly average or worst case rather than best cases. And the space for this algorithm is O1, because we will not require any additional memory to store this, and we can do this in place. That's pretty much it. If you're interested in knowing the nitty gritties of how to implement this, at the end of the lecture, when we have finished discussing merge and quicksort, there are some resources where you can actually see like how the code for this algorithm looks like. Thank you.